I'm recording now, so don't tell me now. Um, I hope you guys had a good break. Some of you got a chance to relax. We're going to need that. No? Well, I can speak for myself. I had a really good break. Uh, I was at a beach, at a water park, at my relative's place, roamed around in Virginia, roamed around in DC. So had a really, really good time. I needed that. Yeah. I've not had a break in a few years now. So, was that? Signal's homework is not due, it's due tonight. Yeah. So, well, you just brought me to a bad place. I was such in a good place, right? Yeah, by the way, nobody is wearing a mask outside like us. Inside, outside, like it's like nothing has happened. No, elevators, hotel rooms, like nothing. So that was a bit scary, but then it's been a few days after I've come back, so I'm still here, which is good. Okay, so while all of this is going on, I hope you guys have noticed that we are sketching something. What are we doing here? We are taking a Fourier transform of everything that is being recorded and heard, right? So that's how my voice looks like. The y-axis is amplitude. The x-axis over here is frequency. So if I speak, that's I'm in the low frequency region, and if there was a girl speaking, maybe the spectrum would shift to a right a little bit, right, because of higher frequency content in a girl's voice. But if I whistle, then what are you going to hear? Just one tone, right? Right there. Yeah. Let us try to measure what that frequency is. About 1.2K. That's the frequency at which I'm whistling. And I can do something funny, like a little bit more interesting with this. Let's see, doing a scan. So I'm scanning that tone, like up and down. And if you have, this is a web-based app, by the way. I just searched for online spectrum analyzer, and this came up. So I'm just using my microphone as an input, and I'm able to do that. Now, if you have a phone, smartphone, which everybody does, you can use like a function generator app on your phone and generate a tone on that, and look at that. So right now I have a sine wave at 1K. And you can see that tone there, right? And if this was a square wave, you not only see the fundamental, you also see harmonics. And as I reduce the amplitude, they all go down. You can do some linear chirping with this. Chirp is a signal whose frequency increases linearly with time. That's a chirp signal. So if I do this, this is a 10-second chirp that starts at 20 hertz and ends at 20 kilohertz. You see that? It scans. And the envelope of those are following a sinc, because the chirp is a square wave chirp. So a lot of fun things that you can do with just your phone and an online-based app. All of this is what? Transforming a signal from time domain to frequency domain, right? Because if I whistled, and if you looked at it in time domain, it would look something like this. enable. Oh, need to use signal. If I whistled perfectly, it would look something like this in time domain, right? This is in time. But in frequency, what did it look like? Just one tone, right? One frequency. So what are we going to learn today? That. How do you transition from time to frequency? And if needed, go back from frequency to time. If you had a computer-based program like MATLAB or Python, you would be able to find out programs that do that for you. Not just FT, not just Fourier transform, but they can also do fast Fourier transform. So algorithms that do the Fourier transform, but very quickly, fast Fourier transform. And they're also, if you read research papers on this, there is a very fast Fourier transform. So a lot of claims have been made. We are going to look at how do you do that Fourier transform on paper. So what I'm going to do here is switch the sharing. Here. Okay. Let's make this guy over here. Let's track this. Okay, big enough. This is where we stopped last time. The slide title was, what information does X of omega provide? And the reason why we stopped at this point is because I thought this needed a new discussion, a start discussion, because this is very, very important. What does X of omega have? Well, simply it answers the first question, right? Frequency is present in the time domain signal. So let's make up our own signal here. Let's say I have, this is time, and this is, say, x of t, right? I have my x-axis as time, y-axis as amplitude of x as a function of time. And let us say I have something like this. Right? What information can you get from this? If you look at it very closely, you might be able to make two statements. One is, there are some low frequency elements in x of t that have a pretty big amplitude. And there are some higher frequency elements in x of t that have a smaller amplitude, right? So two things you can probably say at that point. Now, using that information, you probably get something like this. If your x-axis is now frequency or radian frequency, one or the other, and if you were looking at, say, the magnitude of the Fourier transform of x, right? You took that signal x of t, you did a Fourier transform on it, you got cap x of omega or cap x of f. And now you are doing an absolute, you are doing a magnitude. Why are you doing a magnitude? Because the Fourier transform of a signal can be complex, it'll have a magnitude, it'll have a phase. We are looking at the magnitude. So what can you say about this? Well, you're going to have, because of this guy, you're going to have something pretty high in the low frequency region. And because of this guy, you're going to have something low. In terms of amplitude, it's low, but it is in the high frequency region, right? Now, let's suppose that this was like a continuous time signal that was going on forever. And of course, our frequency is also continuous. So realistically, you would be looking at something like this, right? Something like that, right? That would be the Fourier transform. Lower frequencies are higher in amplitude, higher frequencies are lower in amplitude. That's an example, right? Now, so that is the information that is hidden in x of omega. The frequency is present in the time domain signal. You can answer a lot of things by having that information. For example, how fast should you sample x of t? That is an answer that you can determine right away. If you know x of omega, you know that answer right away. How? All you need to look at is the highest frequency component in x of omega. So suppose it was, instead of going like that, it was something like this. It went something like this. Just an example, right? And say this was 0 over here, and this was, say, f max, right? That's the highest frequency it has, x has. The moment you know this, f max, then in order for you to sample the signal x, what is sampling? You're essentially saying, I will multiply it here, here, here. Regular sampling, right? You're picking out samples every few seconds. But how many seconds? Should you do this or should you do this? Slow, right? Slow sampling versus fast sampling. How can you determine that? Well, there's a Nyquist criteria which says you need to sample at least twice the maximum frequency. So Fs, the sampling rate, should be greater than or equal to twice the maximum frequency of the signal. We know the maximum frequency of the signal from the Fourier transform. What is Fs? Fs is the sampling rate for this guy, right? Which means T is, or Ts is 1 over Fs, right? So if you determine Fs, you can find the reciprocal of it, and you can find Ts, which is the sampling time. That can determine how close should each sample be versus how far should they be, right? So that can give you limit. You can always go lower in time. You can always sample finer. What happens when you sample finer? Good news, bad news, both. Was it? Waste. Yeah. So it's actually both, right? It's good news and bad news. Good news is what? I have a lot more information now than I need. Bad news is I need to store it, I need to process it, I need to deal with a lot more information than I need. So in terms of that, oversampling is bad, right? So what you try to do is you try to stick at very close to twice the maximum frequency. With this, we can also look at a industry standard. You guys hear songs all the time. What are your songs? What is the sampling rate for your songs that you guys listen to? 44.1 kilosamples per second. You guys have seen this on audio CDs, not CDs anymore, but you guys have seen that as a standard, right? 44. Where is that number coming from? 44.1 kilosamples per second. It's greater than twice the maximum frequency a human ear can hear, to 20 kilohertz. Twice that, 40 kilohertz. Just more than that, 44.1. And it also has to do with the size of the CDs, right? That's why that weird number, 44.1. But they're all related to Nyquist, right? You see why is that important? Well, if you sample it lower than that, then you lose important information. Then when you try to reconstruct it from the samples, you will not be able to get your song back. You will have some distortion. If you sample more than that, you will have your perfect song, but the problem is that your hardware now is going to be bulkier. And there is going to be latency. Why latency? Because you now need to process all those information, right? So in terms of latency, you're going to increase latency through the circuit, plus your circuits are going to be bulkier because you're going to have to store all those samples. In any case, that answer, frequencies present in the signal, will help you determine at what rate you need to sample it at. Later on in our lectures, we will have like a very detailed lecture on sampling and reconstructing signals. So stay tuned for that. It's a very interesting one. Next, frequency equalization. This is also a very nice idea. What does frequency equalization mean? Frequency equalization. You're trying to equalize frequency, right? So let's suppose that you have a channel between you and me. What is that channel? Well, for people online, it is the microphone, right? So let's just assume that for this lecture, everybody was online, right? And if everybody was online, between you and me, there is a channel which is established by WebEx meeting and this microphone. Yeah? Now, is that channel perfect? In other words, is that channel treating all the frequencies exactly the same? Maybe, maybe not. Yeah? So let us suppose I was interested in doing this. I was interested in sketching the Fourier transform of the channel that exists between me and the students. Yeah. So what? And that channel will have some impulse response. That impulse response is what? H of t. I took the Fourier transform of that. I got h of f. I'm trying to plot the absolute value of h of f. How would you want this to look like? Well, you would want this to look like this, right? Treat all frequencies the same so that whatever I say is heard by you, exactly the same. Yeah? But that's not true. That's not how it is. It's not like that. It's like this. Something like that. It will have a cutoff over high frequencies. And before the class started, we actually measured it. It was around 12K. Above 12K, my microphone was not picking up any sound. It was not able to pick up any sound beyond 12K. So what can I do with this? Now look at this. Let's try to approximate. The blue lines, I will approximate a little bit for the sake of discussion. I will say this is like this and this is like this. For the sake of approximation, I have sort of linearized it. If I know that that is what the channel is doing to my voice, how can I equalize it? Maybe I can have another element in my transmission chain, either the transmitter all the way to the receiver, that does exactly the opposite of this. It will do something like this. It is going against the blue line, meaning if the channel is lowering the amplitude of higher frequencies, then I'm putting something in my channel that is doing the frequency equalization, reversing that effect, so that if my voice goes through, it will flatten out because the impact of the channel has been reversed by another filter. The pink line is the filter. You can do this before you transmit, or you can do this at the receiver. If you do it before you transmit the signal, it's called pre-distortion. You're distorting the signal before you send. Or you can do post-compensation. After you receive the signal, you can bring up the frequencies, bring up the amplitude of the higher frequencies. And you can do this in software, you can do this in hardware, but most people do it in software nowadays, right? So a lot of digital signal processing ideas that give you what? Frequency equalization, allowing you to see that the receiver sees the same frequencies that are intended by the transmitter. So removing the impact of the channel in the middle. You guys are getting the idea, some flavor there? Okay. Next, filtering specific frequency bands. This is easy, right? A few years ago, maybe like 30, 40 years ago, people, you would sit in their cars and tune their car radios to an FM station. That was 30 years ago. Yeah, maybe 50 years ago. What were they doing? They were literally tuning their receivers, FM receivers, to a specific channel, right? Those channels were where? They were frequency modulated channels, FM channels, right? So channel 1 was occupying certain band. Channel 2 was occupying another band of frequencies. Channel 3 were occupying the third band of frequencies. They were all happening at the same time, right? They were all functioning at the same time, but they were occupying different frequency bands. So in frequency, they were multiplexed, right? In frequency, they were multiplexed. So while you were tuning your FM radio, you were literally changing the center frequency of your receiver filter. Pick up channel 1, pick up channel 2, pick up channel 3. Now, you need to know which channels to pick up, right? So you need to know the Fourier transform of the signals of each channel so that you can design your filters at the receiver appropriately. Again, with this idea of FM, we'll talk about AM with the super heterodyne receiver in detail later on. But I hope you understand that we need that information. So we need to understand the frequency content of the signal. And there are many such applications that are relevant for Fourier transform. You guys have seen Fourier transform where? Circuits, you have seen Fourier transform? You guys see Fourier and Laplace over there as well. You see Laplace, right? You see Laplace, yes. Let's see. So, was that? Yeah, you might have done some Fourier, but you do a lot of Laplace in, right? So the difference is this: one is frequency response, the other is the system transfer function. That's essentially it, right? Okay. But we'll differentiate it here. Polar, the polar form. All right. Let's see. Questions about these ideas? What can you do with x of omega? You can do radio, yeah. Oh, by the way, whenever you talk about multiplexing, right? Think about a transmitter-receiver pair, right? I'm speaking, Ian is listening, right? Suppose there were multiple people speaking and Ian was trying to listen to all of them. How could Ian listen to all of them? What are the different ways channels could be multiplexed? With the FM radio, we talked about multiplexing them or sharing the resource of frequency, right? What other resources could you share? Was it? Time, right? You can do time division multiplexing. Okay, channel 1 speaks for the first 5 seconds, channel 2 next, channel 3 next. Dividing things up in time, but then Ian is going to get bored, right? By that he's interested in channel 2, so he'll have to listen to channel 1, and then he's not interested in that. So he does frequency division multiplexing. It's going to be okay. But then what is the problem with frequency division multiplexing? What is that? Oh, no, the biggest problem with frequency division multiplexing is the big guy, FCC, right? You're going to have to buy the frequency license, right? So you're going to have to pay a lot of money to buy that spectrum. If you're doing it in an unlicensed, like a local region, you will be fine, but you cannot transmit to the whole world at those frequencies. So that's a problem, right? It's costly. Spectrum is money, right? Frequency is money, literally. So we'll have to think about different ways to multiplex. There is space division multiplexing. Antenna here, directed antenna to antenna, directed antenna to antenna. So you are sort of dividing things up in space. You can divide things up in power. Low power, channel 1, higher, channel 2, higher, channel 3. So you can do sharing of resource in space, time, frequency, what else? Power. 4 resources a communications engineer has to multiplex channels. Now, in the context of FDM, frequency division multiplexing, we are going to see some examples there as we go through the lectures. Now, let's come to the core of Fourier transform. How do you find the Fourier transform of a signal? Now, you are trying to find a Fourier transform of a time domain signal, right? So the function itself is a time dependent function. So you see this in red, e to the minus at u of t, right? E to the minus at u of t is the function, is the time domain function. What does it look like? It looks like something like this, right? Yeah. Only for positive time, it's going to be exponentially decaying. Why? Because I chose real part of a greater than 0. Can anybody tell me why did I limit my a to be greater than 0? Good. Because no, not because of it. If a was if a was real part of a was greater than 0, what do you get? E to the negative 5t, e to the negative 10t, right? Something that goes down, decays with time. So if it is decaying with time and you evaluate that integral, it will converge. However, if a was negative, it would go up, right? It would go something like that. It will grow with time. If it grows with time, then you have a problem. The integral will not converge. Fourier transform doesn't exist, right? So that's why we are limiting this to e to the negative at u of t with the condition that real part of a is a complex number, right? So a is a complex number whose real part is greater than 0. This is exactly the same example as 4.1 in the textbook. Now, how do you evaluate the Fourier transform of a signal? Here is our direct formula. Put the signal, the time domain signal in here, multiply by e to the minus j omega t dt and integrate it for all time. You integrate out the variable t, you will be left with omega. Did we derive this? Did we derive this? I think we did. You remember the derivation of this? Where did we get this from? Fourier series, right? So Fourier series, as the time between each frequency element converged, omega tends to 0. We got Fourier series to converge to Fourier transform. You guys remember we did this demo last time with the sinc being sampled finer and finer, and as the square wave was getting farther and farther apart, we were getting more and more continuous in the frequency, right? And as we evaluated that as a omega tends to 0, we got that integral. If you need a refresher, the derivation was at the let's see, right here. So slide 5 from the previous lecture, it's there. The derivation is there. Okay, so what are we going to need? We are going to need this signal to go in here. Substitute. What do you have? E to the negative at u of t. E to the negative j omega t carries over. Now it's a u of t will help you do what? Adjust the limit, right? U of t is going to help you go from 0 to infinity instead of negative infinity to infinity. And for all those places, it is 1, right? So it's just 1 over here. Negative e to the negative at carries over, e to the negative j omega t carries over. Both are exponentials, so you can combine them as e to the negative a plus j omega times t dt. Everybody loves integrating exponentials, and this is a definite integral, so you can substitute the limits. With a real part of a going to be greater than 0, you will get one closed form answer for this, 1 divided by a plus j omega, where a is also a complex number. 1 divided by a plus j omega is the Fourier transform of what? E to the negative at u of t with real part of a greater than 0. So we have derived this particular Fourier transform pair. Fourier transform pair. FT pair. Why pair? Because time to frequency, if you take frequency and you take the inverse Fourier transform, you go back to time. So it's a pair, always a pair. How do you indicate the Fourier transform pair? Double-sided arrow with the Fourier symbol on top. Questions about this example? Going once, twice, sold. 1 divided by a plus j omega. Is it complex? The entire class says yes. All right, so if it's complex, then how can I sketch it? What's that? As a magnitude and phase, right? So I'm going to sketch the magnitude spectrum and the phase spectrum. So x of omega is complex, so it will have some magnitude and it will have some phase. What will the magnitude tell me? It will tell me the magnitude of x of omega as a function of frequency. The phase spectrum will tell me what? How does the phase change with respect to frequency? So in both cases, the x-axis is frequency. Either it be f or it may be omega. They are just related by a factor of 2 pi. So on the left here, we have the magnitude spectrum. On the right here, we have the phase spectrum. And 1 divided by a plus j omega, I am sure you guys know how to find the magnitude and phase for it. The magnitude of x of omega or x of j omega or x of f will be what? 1 divided by the magnitude of the denominator, which is a squared plus omega squared. Right now, I'm assuming that a is a real number, right? But a could be complex as well. Right now, I'm assuming that it is real. 1 divided by square root of a squared plus omega squared. On the phase side, what do you have? You had 1 divided by a plus j omega. The phase of that is what? 0 degrees minus tan inverse imaginary by real, right? Yeah? 0 degrees for the real number. For the right? Phase of this guy minus phase of this guy, right? For this guy, you got 0. For this guy, you got tan inverse omega by a. So phase spectrum should be plotted as negative tan inverse omega by a. And if we do this, if we do like a scanning of omega, right now I have omega going from -5 to 5 in a very small steps, and I have literally sketched it out in MATLAB. So what did I get? I got something like this. I got like a low pass filter kind of characteristic. Not ideal, nowhere close to ideal. In this particular plot, I had a as a parameter. So I chose a to be 1 in this plot. That is why my height over here, instead of this being what? This is omega equals 0, right? If omega equals 0, then you are left with 1 divided by a. So instead of this being 1 divided by a, because I chose a to be 1, outside. All right, so here you got the magnitude spectrum on the left. Then if you did the same exercise, you've got the phase spectrum on the right. And you can see that for a small region in frequency between -1 and 1, the phase is very linear, right? But apart from, what does phase linear mean? Is it a good thing or a bad thing? Phase being linear. Okay, so phase is related to what real, a phase shift corresponds to what in time? Time delay, right? A time delay corresponds to a phase shift, right? So a linear phase shift corresponds to the time delays being linear, which means that if something were to come from here to here, and if they started at 1 second, 2 seconds, 3 seconds, 4 seconds, then they'll come here at t plus 1, t plus 2, t plus 3, t plus 4, linearly. So in terms of time delays, they are going to be consistent. So linear phase is a good news, right? But it is good news only for a small region in frequency. Apart from that, it becomes a non-linear phase, which means that there can be some crossover, right? They're not going to be arriving at all the same time. Okay, so the whole point of this is what? Don't go for simply the Fourier transform of a signal, go for magnitude spectrum and the phase spectrum, right? Try to see that they are two different things and you need to evaluate them separately. Next, Fourier transform of Signum or a sine function. By the way, what are we trying to do with all of these things? We are trying to establish a set of standard Fourier transforms, right? Why are you interested in establishing a standard set of Fourier transforms? So that with the standard set of Fourier transform and the properties of Fourier transforms, you will be able to answer all Fourier transforms, at least all the ones that exist, right? So that's what we did even for the Fourier series. Even for the Fourier series, literally for the Fourier series, we just had 2 or 3, right? We had square wave, impulse train. I think that's it. Those were the only 2 standard forms that we had. All the other things were properties. Right now we had some decaying exponential for the Fourier transform, and this is the sine function or the Signum function. We are trying to evaluate the Fourier transform of that. Now, how is it defined? The sine function is defined as it is going to be -1 for time less than 0, and it is going to be +1 for time greater than 0. So it is sketched this way. So -1 for time less than 0, and it is +1 for time greater than 0. Positive sign, negative sign, -1, +1. That's why it's called the sine function. Now, there's a discontinuity at time equals 0, right? There's a jump from -1 to 1. There's a discontinuity over there, which is going to create troubles when you start integrating things out. So this signal is not absolutely integrable because of that discontinuity. So what can you do? You can use some tricks to find the Fourier transform of this particular signal. And this trick is sort of a unique trick, which is why we are discussing this trick here. The way you are going to evaluate the sine function is by applying a limit. So you see, you are defining the sine function as limit a tends to 0, some x tilde of t. What is x tilde of t? It is e raised to at for time less than 0, and it is e to the negative at for time greater than 0. So it's defined as some exponentials, but as a tends to 0, what happens? This guy will become that, and this guy will become that, right? As a tends to 0, this particular x tilde of t will tend towards sine of t, sine function. You guys see that? So instead of evaluating the Fourier transform of sine function, we are trying to evaluate the Fourier transform of this x tilde function with the limit a tends to 0. So let's try to do that. For x tilde of t, we have cap x of omega with the tilde. Next, for all the time that is negative, we have got negative. This negative is coming from this guy. Integration is from -infinity to 0. The function is e to the at. The Fourier transform is e to the negative j omega t dt. That stays from the Fourier transform definition. Plus 0 to infinity for the positive sign, where the function is e to the negative at, e to the minus j omega t dt. If you, again, do the same thing, what is that? Combine the 2 exponentials, integrate, definite integral, substitute the limits, you will get 2 functions here. And you can combine them to get 1. And now if you evaluate that as limit a tends to 0, you will get the Fourier transform of the sine function as 2 divided by j omega. Again, complex. In fact, it is purely imaginary. So you can find out the magnitude and phase for this as well. Questions here? How do you find the Fourier transform of e to the negative at u of t with the real part of a greater than 0 and the sine function? Now, if I do nothing else for the rest of the lecture, and if I give you some signal, will you be able to find the Fourier transform of it? Maybe you will have a really, really tough time doing it, but can you do it? I think so. You may have a really, really tough time doing it, but you should be able to do it. How will you do it? If we didn't have any lecture, would you be able to find any time domain signal if I give you in closed form, in a mathematical expression? Will you be able to find the Fourier transform of it? All you have to do is what? Use this, right? Not this, this. So if nothing else, you know this, right? That is the definition. You put in the time function in there and you evaluate x of omega. Once you have x of omega, you have magnitude and phase of x of omega. So you know the tough way to do it already. We are just trying to make it easier now. All right. Next, okay. Fourier transform of m times rectangle of T1. It's a rectangle. What is the Fourier transform of it? All right, this you should know. Come on. Go ahead with confidence. Let's go. All right. Right. So we know the answer. It should have some sinc. Let's see if it is. So here we have a rectangle with the height of m, and the parameter of the rectangle is T1, meaning it is m from negative T1 to T1. I need to find the Fourier transform of this guy. And because I know a little bit of a background about square waves, I know that it is going to be a sinc shape. So let's try to see if we can get that. I have already defined that x of t is my time domain. And if I take the Fourier transform of that, I get cap x of omega in the frequency. So let's go. I'm going to zoom in over here and do my work there. Cap x of omega equals negative infinity, infinity, x of t e to the negative j omega t dt. I've got that Fourier transform integral written out. I can make it a little bit easier by integrating from what? Negative T1 to T1. What is the value? Value is m, right? For x of t, it is m over there, e to the negative j omega t dt. What is that going to equal? M e negative j omega t divided by negative j omega t1 negative t1. Substitute the limits. What do you get? M e negative j omega t1 divided by j omega positive e. This becomes plus m divided by j omega. I will do some rearranging in the middle here. I get what? E j omega t1. That's it. Minus E minus j omega t1. All right. What is that thing in the middle? Two j sine omega t1. Agree? Using Euler's. Yeah? So I can continue here by saying this is the 2m, the j cancels out, 2m divided by omega sine omega t1, right? That's the Fourier transform. Oh, we said sinc. Is it a sine? Is it a wrong answer? No, it is the right answer. In fact, it is the form you have written out in your tables. It is the same form. But you can translate it into a sinc by doing what? Right? Multiply and divide by T1, right? Because you wanted this omega T1 here, sine x by x. So you needed that x. All right. So what is this becoming? This is going to become 2m T1 sinc omega T1. I can box this up. M is just controlling the height, right? So if M was 1, you would get 2t1 sinc omega t1. Very similar to the Fourier series of a square wave, right? For a square wave Fourier series, you got what? 2t1 divided by t sinc k omega t1, sinc k omega naught t1. You're getting the same shape here, but you're just not getting it the sampled version of it. Questions about how do you find the Fourier transform for a rectangle? Okay. What is the Fourier transform of a sinc signal? A rectangle. What is the inverse Fourier transform of a sinc? A rectangle. What is the inverse Fourier transform of a rectangle? Sinc. Pairs, right? Fourier transform pairs. You see rectangle, you know sinc in the other one. Let us try to do something else. Look at it in time. Can I say that this is a time-bounded signal? It's bounded in time. Yeah. How about frequency? Sinc goes on forever, right? So bounded in time, unbounded in frequency. Can I do it the other way? If it was, of course, we just said if it was sinc in time, then it was rectangle in frequency, right? So what I'm trying to drive home is this. If a signal is bounded in one domain, it is unbounded in the other. Okay? Now let us try to see. Ideal filters. You guys have done ideal filters, discussion on ideal filters in circuits maybe? Yeah? Ideal filters have what kind of frequency response? Sharp, edge, rectangle, right? So for that, their impulse response should be what? Their impulse response should be sinc, goes on forever. Is it practical? No, absolutely not. So what do you do in that case? You limit it. Instead of going for infinity, that sinc is limited to maybe 3 cycles or 4 cycles. So when you limit it, there is a corresponding effect in the frequency domain. What is that? Instead of being sharp, it will now have a roll-off, a transition band. You guys see that? So that's how those ideas are linked. Okay, let's go to the next one. A Fourier transform of a rectangle is a sinc. All right. So this can go on a t-shirt, right? So this can be like a signals and systems t-shirt. Fourier transform of a rectangle is a sinc. How do you define a rectangle in bracket notation in the time domain? This way, x of t is 1 between negative t1 and t1, right? This is just to say, what is that? T1, negative t1, t1, right? That's that. And for all the other times, it is 0. So if that is your function, which is sketched over here, the Fourier transform of that is going to be 2t1 sinc omega t1. When we just proved this with m equals 1, that's what we had. Now let's do some interesting things with this. What is the area under x of t? What is the area here? Uh, 2t1, right? With the height as 1. What? Height as 1. If the height is 1, then it is 2t1. All right, so the Fourier transform of this guy looks what? Looks at like this, right? The area under the curve in one domain is actually the value of x of omega at 0 frequency. And it goes the other way as well, area under x of omega. And now you know that area under the sinc should be 1. It'll be 1 divided by 2 pi. Sorry, it'll have a factor of 2 pi. I'll tell you where this is coming from. It is coming from this definition. You just plug in omega is 0. This will go away, and you got what? Area under the curve, right? So area under the curve in one domain will give you the value of Fourier transform at DC, right? 2t1. You guys see that? And now you can actually use it the other way as well. But you are going to have an issue. What is that? The factor of 2 pi. Let me show you where that factor of 2 pi is coming from. If you look at the formula to compute the inverse Fourier transform right here, if you have the Fourier transform of a signal, you can find out its inverse Fourier transform by using this. Again, we have proved this by using the Fourier series convergence. So if you need 0 time, you put in 0 here. This cancels out, but you got what? Area under the curve in the frequency domain divided by 2 pi. 1 divided by 2. So let's go back. If this is the signal, its Fourier transform is this. If the question was, what is the area under this sinc? You know it's 1 divided by 2 pi, right? Because the value here is 1. Can you see that? Yeah. I don't need to look at anything else. I just need to look at the area, and I know the value at 0. All right. That's what I'm calling as an interesting result here. Area under the time domain signal is the same as x of 0, cap x of 0. Cap x is used to denote the Fourier transform at omega equals 0, which is the same as f equals 0. The value at omega equals 0 in the frequency domain. And you can prove this by simply substituting the value of omega or f as 0 in the Fourier transform integral. X of omega equals integration of all time, x of t e to the minus j omega t. Substitute omega equals 0 over there, and you get your result. However, when you want to go back, it is area under the frequency. How do you find out the area under the frequency domain signal in the sinc? You take the value of it in time as x of 0, and you divide it by 2 pi, and you get it. So we had 1 divided by 2 pi in the previous case. No. No. There's a problem here. Plus. Is that right? If that is the case, and if I plug in t is 0 here and here, area under the curve will be x of 0 multiplied by 2 pi. Multiplied by 2 pi. Is that right? Yes. So over here, it will be 1 multiplied by 2 pi. So it will be 2 pi. 2 pi is the area under the curve there, sinc there. All right, questions about this. How do you find the Fourier transform? How do you find the value of the signal in the other domain at either omega equals 0 or t equals 0? Just find the area under the curve in the previous one. Looks like a really good problem for like a short answer question on exam 2, huh? All right, let's move on to other transforms. Transforming delta functions. Let's go back to the king of all signals discussion in the first lecture. Ian said sine function was the king. I disagreed. I said impulse function is the king. And my reasoning was that it goes for all amplitudes and all frequencies. Goes from 0 to infinity, and it goes for its frequency responses flat. It is consistent for all frequencies. So let's take a look at that impulse function. What is the Fourier transform of delta of t? Well, substitute it in your Fourier transform integral. You get that integration over all time, delta of t e to the negative j omega t dt. Whenever you are multiplying a time domain function with an impulse, what do? You evaluate that time domain function at the time for which the impulse is valid. When is this valid? This is valid only when t equals 0, right? So you evaluate this guy at t equals 0. What do you get? 1. So you're integrating 1. You've got a 1. I see that? All right, let me equals integration delta of t e minus j omega 0 dt equals integration delta of t 1 dt. Integrating over an impulse. 1. Yeah? What does that mean? If you sketch it out, let us try to sketch it out over here. In the time domain, you have got an impulse. Yeah? In the frequency domain, what is it going to look like? Oh. This is frequency Fourier transform. Fourier transform of delta of t is 1. This is omega. Yes? Similarly, you can find the inverse Fourier transform of delta of omega. What is delta of omega? It's an impulse, but in the frequency domain, right? So how can you sketch delta of omega? You would make this omega, you would make this omega, and you would get delta of omega. How can you find the inverse Fourier transform of that? Well, inverse Fourier transform of a function is 1 over 2 pi integration over all frequencies delta of omega e to the plus j omega d e to the j omega t d omega. You are integrating out omega to get your time back. What is this going to be? Again, you do the same thing. D delta of omega multiplied by e to the j 0 t, that will be a 1. You are integrating over an impulse, you will be left with 1 over 2 pi. So what can you say about this? Inverse Fourier transform of delta of omega is 1 over 2 pi. Yeah. If I multiply 2 pi on both sides, what do I get? This guy goes out, you get 2 pi times, you get this, right? In the time domain, you have 1. In the frequency domain, you have 2 pi times inverse, 2 pi times delta of omega. You see that? So if you have a 1 in the time domain, in the frequency domain, you have an impulse, but with the weight of 2 pi. You guys see how we got this? We first found out the inverse Fourier transform of delta of omega. We got that to be 1 over 2 pi. So if inverse Fourier transform of delta of omega is 1 over 2 pi, then you can write this, right? You can write 1 over 2 pi delta omega, right? Yes? You multiply 2 pi on both sides, you get this. Can you say that? Can you multiply, if you multiply a time domain signal by m, is it the same as multiplying it in frequency by m? Can I say that? Absolutely, right? Because you see, it's an equation, right? If you put a 2 in there, that's like putting a 2 in there. Sure, it comes out. All right, question so far for an impulse is good? Good. It works out the same, but then you will have a phase. Phase spectrum will change. Yeah. So you will have a e to the negative whatever phase that is going to get added. So Was that? Magnitude is the same, yes. Magnitude is the same, phase gets shifted. So that's a property we are going to look, frequency shift property, we are going to look at that as well. Oh, time shift, there's also a frequency shift. So we'll look at both angles of the same thing. Now, let's try to find out the Fourier transform of a unit step. Fourier unit step has the same problem as sine function. What is that? It is not absolutely integrable. Why is that? There's a discontinuity, right? Because of that discontinuity, we are going to have to deal with the unit step in slightly a similar way as we did with the sine function. But because we already did some work for the sine and we got the result, let's use it. So u of t, the signal that is shown on the left, can be written as a summation of half of the sine function plus a constant half. You guys agree with that? Can you break it up? Because you see, for all the time that is less than 0, negative half, positive half, 0, u of t. Half, half, 1, u of t, right? So u of t is being written up as half of the sine function and just a constant half. And we are using these two because we know the Fourier transform of these two. So we can say if x of t is u of t, a unit step, we can write this as x1 plus x2, half of sine function plus half constant, and the Fourier transform of that is going to be what? For half, we get the half. Let me sort of do this. For this half, we got that half. Yeah? And then for this half, we got all of that. For sine, we had derived that to be 2 divided by j omega. The only thing that is sort of out of place is this, right? Need to change it. All right. Questions here? We found the Fourier transform of sine as 2 divided by j omega. If you multiply by half here, you multiply in the frequency also by half. For just the half, we are using this, right? If you have a 1 in the frequency, you have 2 pi delta of omega. If you have a half, you have a half there, right? So that's how we are getting the part in the green. Now you can simplify this a little bit. What do you get? You get 1 over j omega from here, and you get pi delta of omega from here. So the Fourier transform of a unit step should be written in a bracket notation. When omega equals 0, you get pi delta of omega, only this piece. And when omega doesn't equal 0, you get this 1 over j omega right here. But both combined, you write it this way. 1 divided by j omega plus pi delta of omega. Exactly. Yeah, exactly. So if you just want to write it as an equation, you write it on the left. But if you want to write it as a bracket notation, you have it on the right. Yep. Other questions? Good. So L'Hopital rule, right? So you get a 0 over there as that is going. So that will simply be pi delta of omega. Other questions? So we've got impulse, we have got unit step, we have got sine, we have got a decaying exponential of a few transforms already. Now let's start putting in some properties. The list of properties is going to be a little bit longer, but the good news is this. You have seen most of these properties play out in the Fourier series. Linearity property. We have secretly been using this already. Right here, we have used it. Right? Half of this plus half of this. I've used linearity property already. Let us try to formally use it and prove it as well. we are given that there is a signal x1 whose Fourier transform is cap x1 of omega, and there is another signal x2 whose Fourier transform is cap x2 of omega. If we are given that, then if A and B are constants, ax1 plus bx2, another time domain signal, will have a Fourier transform as A cap x of 1 of omega plus B cap x2 of omega. They're individual Fourier transforms that have been scaled by the same constants. And you can prove this easily. How is that? By using the definition of Fourier transform integral. So let x3 be a new signal that is the scaled and summed version of x1 and x2. And if you try to find the Fourier transform of that, you plug in the entire x3 over here, multiply by e to the negative j omega t dt as is, integrate out the time, you will be left with omega. And because of this integral, you can break it up into two integrals. A is a constant, comes out, integration over all time, x1, plus b is a constant, comes out, integration over all time, x2. All of this is x1. All of this is cap x2. So that essentially proves your linearity property. Questions here? I've seen this, done this many times. You guys see that we have used linearity over here, right? We have used linearity over here, we just didn't treat it formally. But we have proved it here now. Next, time shifting property. All right, so this brings to Colin's question about what if the delta was shifted? So before I start talking about time shifting property, I'm going to talk about something more general. What is that? Whatever you do in time domain, whatever change that you do in time domain will have some change in the frequency domain, right? If you play with x of t, you will mess with cap x of omega as well. We just need to figure out what that change is, right? Here, if you delay the signal by some amount, t0, by 5 seconds, by 10 seconds, then what are you doing in the frequency domain? You are literally multiplying by a phase term, e to the negative j omega t naught. What is omega? It's a variable, right? So on this side, the Fourier transform is a function in omega. You've got a function in omega here. This is also a function in omega here. But there is a dependence on time. If you delay by 5 seconds, you will have a 5 over here, e to the negative j omega 5. So there's no change in magnitude. Why is that? Magnitude of this complex number is what? Magnitude of this multiplied by magnitude of this. Magnitude of this guy is always going to be 1. So there is no change in magnitude, but there is a change in phase. Yeah? Looks like another short answer question. All right, how do you prove this? Let x3 be a signal that has been delayed. So not delayed, I should say shifted, because t0 can be positive, can be negative. X of t minus t0 is x3. We are trying to find out its Fourier transform, and we are calling that x3, cap x3 of omega. So cap x3 of omega is Fourier transform of x3 of t. x3 is simply x of t minus t0. You continue to have e to the minus j omega t dt as is from before, and now you do a change of variable, because I don't like the t minus t0. I want it to be one-time variable, maybe tau. So change of variable, tau equals t minus t0. With that, you can change the lower limit, upper limit, and dt will become what? D tau, right? dt will become d tau. Lower limit, negative infinity. Negative infinity to infinity is going to remain as is, right? So the limits will not change. dt will become d tau. But now you have t minus t0 going to tau. So limits have stayed the same, x of tau, e to the minus j omega, tau plus t0 instead of t, d tau. Now what can you do? You can bring out the j omega t0 term, because t0 doesn't depend on tau. You can bring it out of the integral. Tau remains as is. You've got this out of the integral. All of this is what? X of tau e to the minus j omega tau d tau, the Fourier transform of x, right? So that proves the time shifting property. Again, time shifts in time domain interpreted as phase shift in frequency domain. Questions here? All right, so let's try to do this. Just for fun, what is delta of t, Fourier transform? Good, 1? All right, so what is the Fourier transform of delta of t minus t0? Was it? No. Yeah? Questions about these three things? I've just used the Fourier transform of an impulse and the time shifting property to get these three. Let's box this up over here. All right. This is definitely a short answer question. This was that? Yeah, this whole lecture is like short answer 5-pointers, right? Nice tricks involved in this problem. So we are going to need to find the Fourier transform of e to the negative 2t plus 1 multiplied by u of t minus 2. Okay, so think about this before we start talking about the solution. Think about this individually. Here, u of t minus 2. How could you do, if you were asked to find the Fourier transform of u of t minus 2, how would you do it? Two things: Fourier transform of unit step, time shift, right? So you would do these two things and you would be done. Yeah? Okay. How about this? E to the negative 2t plus 1. How would you deal with that? Was that? So try to use the first thing that we derived, e to the minus at u of t, right? With real part of a greater than 0. Right now 2 is greater than 0, so we are good. We would try to use that, right? So we are going to need to do what? Can we change anything here? We can't change anything here because it's a unit step that has been delayed by 2 seconds. We can't do anything here. However, we may be able to play some games over here. How? So if we wanted this, how do we actually want this to look like? We want this to look like e minus 2, but do you want t? No, you want t minus 2, right? You want something like that, so that when you shift, when you apply the time shifting property, you apply to this, you also apply to that. You guys see that? So you want this exponential to be manipulated in such a way that you get something like this. E to the negative 2, t minus 2, because this is t minus 2. You want that to be the same. So that when you do the time shifting property, it applies to the entire signal. But in order for this to be the same as this, what do you need? You need to multiply by something. What is that? E the negative minus. So you got what? E the negative 2t, oh, plus 1. Over here you have got plus 4, right? Okay, so plus 4 needs to become minus plus 1. You guys see that? So we have represented this signal over here with this signal over here. The idea was we wanted this to be t minus 2. We didn't want t, we wanted t minus 2. Why? Because this was t minus 2. so that once you express it in this way, you can apply the time shift property to the entire thing. You see that? Now let's try to look at, so all of this has been explained over here. We have written x of t in this form, e to the negative a times t minus 2 plus b u of t minus 2. And then you have tried to compare coefficients to get a and b. A and b came out to be 2 and 3. We did that already. We already did that, but we did it directly. So we need to find the Fourier transform of this guy, right? How do you start? You don't start with the final one. You start with something like this. E to the negative 2t u of t. You start with that. And then you put in unit operations. Take a look. You start with e to the 2t u of t. Fourier transform of that is 1 divided by 2 plus j omega. We know that. That was the first Fourier transform that we evaluated. Next, let's do a time shift by 2. When you do a time shift by 2, this becomes t minus 2, that becomes t minus 2. But that is happening in the time domain. So in the frequency domain, you are going to have to multiply by e to the minus j omega, j2 omega. That's the time shift property. Yeah. Next, this is not what we want. We still have a e to the minus 3 to account for. So you multiply e to the minus 3 over here, you multiply e to the minus 3 over here. So the Fourier transform of the signal that we started off with is this. You see that? So just manipulating the exponents so that you will be able to use the standard forms and the properties. Questions about this example? Going once, going twice. You guys are silent today, online and in person. No questions? It's that easy. All right. Fine. Really, that straightforward, huh? All right. Let's try to, was that? Yep. Let's see, the Fourier transform. All right, so let's try to deal with this problem. Fourier transform of this signal. What is this? The answer is going to be what? Full of blanks, sinks. Good. Are they going to be good sinks or bad sinks? Nice looking sinks, or that has a phase term in there, that has a phase term in there, phase terms in there, right? Because of the time shift, they're not centered at 0, right? So they're not going to be well-behaved sinks. They are going to be very naughty sinks. But they are going to be two sinks, right? One for this guy, one for this guy. This plus this. So you are going to have to use linearity and time shift properties to deal with that. So let's try to break it up. Break it up as decompose into two signals. You have got one rectangle over here, and you have got a small little rectangle over here. If you add them both together, you get back your original signal. So you're decomposing that into two signals. Why? Because I know the Fourier transform of this guy, and I know the Fourier transform of this guy, at least the shape. Forget about the time shift. I know the shape is a rectangle, so I know that in frequency it's going to be a sinc. Now, let us try to use the known transforms. What are the known transforms? If I have a rectangle that is starting at 1 and ending at 4, it is 3 seconds or 3 time units wide, right? And if I wanted that to be centered at 0, then I would consider something like this, negative 3 over 2 to 3 over 2 with a height of 1, right? So that it's centered around 0. The Fourier transform of this guy is what? 3 sinc 3 by 2 omega. What did I use here? I used this. 2, what is that? 2t1, right? 2t1 sinc omega t1. What is that? 2 sinc. Let me just go back and check. M is 1 here. Right. So m is 1, 2t1 sinc omega t1. Right. So t1 is what? 3 over 2 in this case. So if t1 is 3 over 2, you put it there, you get this, right? 3 sinc 3 by 2 omega. That's your known transform. That will help with this guy. Next, there's another shorter one. I'm considering it as a height of 1, but I need to scale it to half later on. Over here, t1 is what? T1 is half. If I plug in t1 is half in this, I get sinc half of omega. So I've got the Fourier transform of pulse 1 and pulse 2. Can you guys tell me the relationship between x1 and pulse 1? Is that okay? All right. Let's do pulse 2 and x2. 2.5. Is that okay? All right. X is x1 plus x2. X1 is P1 of t minus 5 by 2, plus we needed that half because this was 1 and this was half. So we needed that extra half in there. P2 of t minus 5 by 2. Yeah? What is the Fourier transform? What is the Fourier transform of P1 of t minus 5 by 2? P1 of t, Fourier transform is P1 of omega. Time shift gives me that. Yeah? And then this time shift will give me that. This half will give me that. I had already written out P1 of omega and P2 of omega. Substitute, simplify, you get that. There are two sinks that are not well behaved because of that exponential, right? They are shifted. Questions about this? How do you deal with rectangles and all that have been shifted, scaled differently? So any rectangle, any width, any height, any combination of rectangles, you guys are going to be okay with that? Now, if you are sort of, you have time and you want to practice a Fourier transform, try to do this. Try to develop a pattern with this, right? A staircase. How would a staircase that starts at 0 would look like, right? Something like this. Goes up, goes up, goes up, goes up, goes up. How do you deal with something like that? Can you find the Fourier transform of such a signal, but express it as a pattern, as a summation? Think about that. It's going to use some ideas that we just talked about. One rectangle, 2 of them shifted, 3 of them shifted, 4 of them shifted more, 5 of them shifted more, and keeps going, right? So you can express the Fourier transform of that as a summation. Try that if you want some practice. Other questions about this? Fourier transform of unit step, we did this already. All right, disregard this because we have already done this. Next, time differentiation property. All right, this is new. I always will start with a property the way I started with the time shift property. Some things that you tweak in the time domain will have something else changing in the frequency domain. You did a time shift, you had a phase term. You're differentiating in time. If you differentiate in time, you will multiply by j omega in the frequency. very similar to the Fourier series time differentiation property. However, over there, we divided by j omega and we were okay. Over here, we cannot divide by j omega. We have to integrate back our results. So how are you going to derive this? Let us try to see the definition of inverse Fourier transform. What is that? X of t is 1 divided by 2 pi, integration over all frequencies, x of omega e to the plus j omega t d omega. That's your definition of inverse Fourier transform. That was derived again by the convergence of Fourier series. The position of x of omega in the integrand implies x of t and x of omega are Fourier transform pairs, right? The fact that there is a function over here, there's a function of omega, that implies that it is the inverse Fourier transform of x of t, right? It's the Fourier transform of x of t. So if you differentiate x of t, what are you going to get? X of omega, j omega, multiplied by e to the j omega t d omega. The position of this guy will reflect that this is the Fourier transform of this entire thing. You see that? It is the position of the function of omega. So in this case, in red, you have what? X of omega e to the j omega. Where is that e to the j omega is coming from this guy, right? E to the j omega t differentiated with time. So by using those two, you can say that if you differentiate the signal in time domain, you are essentially multiplying the Fourier transform of the signal by j omega. Are you changing phase in this? Multiplying x of omega by j omega, are you changing phase? Yes, absolutely changing phase. Are you changing magnitude? Why are you not changing magnitude? You're changing magnitude as well, right? There's omega, j omega. So j is changing the phase, omega is changing the magnitude. So they're both being changed if you differentiate. All right, let's see. Okay, so that's your time differentiation property. But to complete this differentiation process, we also need to look at the integration property, because we cannot just simply divide by j omega and be done, as we did in the Fourier series. Let's try to evaluate the Fourier transform of a delta function, but slightly using a different strategy. What is the delta function? Delta function is the derivative of unit step. We know this from lecture 4, 5, somewhere around there. If you differentiate a unit step, you get an impulse. So the Fourier transform of an impulse is going to be the Fourier transform of derivative of unit step. The derivative of unit step, the derivative function will make sure that you multiply by j omega. The Fourier transform of unit step is this. We know that from earlier. Yeah? So we are trying to use the time derivative property and the Fourier transform of unit impulse to do this. When you multiply these two out, what do you get? 1 plus pi j omega d omega. Is this equal to this or not? Why is it equal? The impulse is only valid at omega equals 0. So that goes to 0. All right, which is consistent with our Fourier transform pair for impulse, right? Earlier we had delta of t going to a 1 in frequency. We have the same as before. Next, time domain convolution. Can we do this in the next 4 minutes? We have it? All right. Rectangle, sinc. Convolution, multiplication, right? And it's a transform pair. So we already know the result. If you convolve two signals in time domain, you will be multiplying their Fourier transforms in the frequency domain. How do you prove it? The Fourier transform of x1 convolved with x2. What kind of convolution is this? Continuous. And what type of multiplication is this? frequency by frequency, right? So each frequency being multiplied by each frequency. All right, so if this is the continuous time convolution, we know from our convolution integral that represents the convolution between x1 and x2. Integration over all tau, x1 of tau, x2 of t minus tau, d tau. Same formula that we have been using for continuous time convolution earlier. The others are what? This integral e to the negative j omega t dt, that is for the Fourier transform, right? So you're taking the Fourier transform of two signals being convolved. And the two signals being convolved, you wrote it over here with the convolution operator, you wrote explicitly, wrote them out as an integral over here. Next, change of order of integration. Instead of doing d tau first and then dt, you're doing dt first and then d tau. And when you change the order of integration, you can bring out the x1 of tau because it is not a t-dependent function. So you can bring the x1 of tau out of that. Then you have integration with respect to t. What is that? x2 of t minus tau will be there. E to the negative j omega t will be there. You're just changing the order of integration. So evaluate this as an integration with respect to t first. Whatever you're left with, that will be integrated with respect to tau after you multiply it with x1 of tau. That's next. But all of this is what? This is simply the Fourier transform of x2 of t minus tau, right? T minus tau e to the minus. So it's exactly the same thing as the Fourier transform equation, except this is your time domain signal. So this would be Fourier transform of x2 of t minus tau. What is x2 of t minus tau? Using the time shifting property, we can say that it is x2 of omega multiplied by e to the minus j omega tau, using the time shift property of Fourier transform. Now, let's backtrack. We are still left with this integration, x1 of tau is there, all of this solved to this. So we can plug in x2 of omega e to the minus j omega tau d tau. Now, x2 of omega doesn't have a tau. Got it outside the integral, left with x1 of tau e to the minus j omega tau d tau. All of this is the Fourier transform of x1, lives with x1. Literally, it's a multiplication of x1 of omega and x2 of omega. Questions here about the proof of time? Oh, time domain convolution property. Why didn't I just call it a convolution property? Because there could be the convolution in frequency domain, right? So the convolution, I need to specifically say I'm convolving the signals in time, which corresponds to what in frequency? Multiplying the two Fourier transforms in the frequency domain, right? So convolution happening in time. Second column, frequency. What is happening? Multiplication is happening in the frequency domain. If multiplication was happening in time, what is happening in frequency? Convolution is happening in frequency, right? Always think about it as pairs. Whatever is happening here, the reverse is happening here, right? Multiplication, convolution, and you can switch it. Let's see. Oh, where can this be useful? Time convolution property. Suppose you have an LTI system, right? Your input is x of t, your impulse response is h of t, the output is what? Y of t. How do you find y of t? You convolve the two signals. Sometimes it can get really, really messy. The alternate would be what? Use the time convolution property. Go to x of omega, h of omega, multiply the two. Simpler. You get y of omega. You need to take the inverse Fourier transform. But maybe that inverse Fourier transform might be easier than doing the convolution. How do you know? You have to predict. While doing the functions that you're given with, you have to sort of see a few steps ahead. If I multiply this with this, I will be left with a rectangle. And if I'm left with a rectangle, the inverse Fourier transform of that is going to be a sinc. And I know that from the standard pairs. So that might be much easier than actually doing the convolution. So see that? So you'll have to sort of think for a minute, look at the signals, how will they play out, the options that you have, and then actually go through solving them. Okay, we will stop here. I'm going to stop recording. I will see you guys when? Thursday, exactly. I will see you guys Thursday.